thank you, Fabrice, and thank you. Thanks. I would like to thank the organizers for this invitation. And I would like. So the motivation of this work comes from. So I am a numerical analyst, and I am particularly interested in the qualitative behavior of numerical schemes. So over a long time. And I will explain this in more details, but if I wanted to find some results concerning the long-time behavior of numerical schemes applied to Vlasov equations, nonlinear transport equations. So the idea, this long time is driven by the Landau damping effect. So the very first thing I did was to open the Mouot-Villani paper, and the idea would have been to add two supplementary parameters, the discrete parameters, the time and the space. And so you don't want to do this, of course. So I tried to find some simple example where you can study the long time behavior, so the Landau damping in a simpler way. And this is a Vlasov HMF model. So in some sense, this is the simplest Vlasov model. I will explain this. And the second motivation is I really wanted to play with the Hamiltonian structure of the Vlasov equation and try to do some normal forms. And in the end, it is a complete PDE technique. It has nothing to do with dynamical systems, but I will give a kind of interpretation of the Landau damping in terms of normal form. Okay, so this is the introduction. So I will start with something extremely basic, just essentially to introduce the notations. So when you have a dynamical system, you can be interested either in the computing trajectories or computing the statistic of solutions. And from the numerical point of view, it is very different because you have to solve an ODE. You don't have pointer, but to a dynamical systems, you can also associate the transport equation. Which means that if you want to look at the statistic of the solution, so the evolution of an observable on the dynamical system, then you end up with the Liouville equation. And in the Hamiltonian case that I will consider in the rest of the talk, so the transport equation can be written this way. So here, this is the microcanonical Poisson bracket. X and V are so X is the space variable and V is the velocity variable. So if you have a dynamical system, which is Hamiltonian, you can write it this way. So J here is a symplectic 2 matrix. And because it's a divergence-free, essentially the Liouville equation and the transport equation are the same. So Kolmogorov, Fokker-Planck, what you want, up to a sign. And you can write it this way. And in classical mechanics, typically you will have such a Hamiltonian here, with a kinetic quadratic part and potential part. And then the transport equation is written this way. Okay. And here you recognize the transport equation of that will appear in the Vlasov equation. Okay, so these are transport equations for if you have a fixed Hamiltonian. But now, if you want to make some simulations on very large system, then when n becomes extremely large, essentially you cannot you cannot use solvers for the corresponding PDE. It's just impossible because you cannot solve the transport equation in dimension more than 10 essentially. And so then you have to rely on other models. So you make some kind of homogenization, and you end up with a hierarchy of models, so kinetic, Vlasov models, etc. And in many cases, so I will give you some examples. Then you have for this nonlinear transport equation. So it just means that you will have a low-dimensional transport equation here, means that here x and v are just will be of dimension 1 or 2. But the Hamiltonian is no longer constant in terms of f. So the Hamiltonian h here depends on f, on the function f. So typically, the nonlinear transport equation I will consider are these ones. It can be written this way. And HCal is an energy. And usually, this Hamiltonian here is the Frechet derivative of a huge function. So you inherit from the classical mechanics, you inherit a sort of Poisson structure. So the very first example are the 2D Euler equations on T2, or but in 2 dimensions for sure. So if you in 2 dimensions, if you look at the Euler equation like this, then in fact, if you impose to be of divergence free, then you are Hamiltonian, and this is the magic of dimension 2. So then, if you just take the vorticity of u, you can rewrite the equation this way. So the vorticity is transported by the velocity field. And then, if you write essentially the Biot-Savart, you will end up with the fact that the Hamilton u is Hamiltonian, and the Hamiltonian is just the inverse of the Laplace of omega. So the Euler equation can be written this way in a very condensed way. And it has the structure I presented before in the sense that this is the Frechet derivative of the energy. So this is, which is quadratic in this sense. And in fact, there is something very strange in all these things, because if you have a Hamiltonian vector field, in fact so if you define this operator, so you take the Poisson bracket, so the transport operator. Then, if you look at the commutator of two guys like this, if you look at the operator associated, then it is the same as the commutator of the two operators. Okay. So in fact, all these equations have Lax pairs. Oh, the Lax pairs are just given by this operator. Probably just saying this you just cannot do anything with this Lax pair. But essentially, this way of writing the equation just is the same as if you write it using this formula in terms of the operator. It is just saying that you have Lax pairs. So it looks integrable. You have Lax pairs. But that's all. Yeah. But okay, so now all these equations all these equations written this way have Lax pairs. But I think that it just say more. It does not really say more than the fact that you preserve the volume in some sense, and the Hamiltonian character of the flow, and in fact that you have the preservation of all the LP norm. In fact. So this is the Hamiltonian structure of the nonlinear transport equation I consider. So this defines here a huge Poisson bracket between two functionals, and you recognize here the right-hand side of the nonlinear transport equation. And so another way to write this equation is just to say that for all functional, the evolution of the functional is just given by the Poisson bracket with the h, where h is the Hamiltonian considered. And so it is just an add operator. So this is a very beautiful structure that you have for fluids and for the Vlasov equation. Of course, the energy is preserved, and if you look at all the observable that are made of g of f, so integral of g of f, then in fact the Frechet derivative is g prime, and g prime of f commute with f, so they just cancel. So you have an infinite number of invariants, which from the numerical point of view is of course complicated. So in particular you have all the LP norms. So in the Vlasov case, the functional h, the h of f is v squared divided by 2 plus a potential that depends of f, and it depends on f through a convolution here in x in the x variable. So you have a kernel here, P, and the Vlasov-Poisson equation, so the P is just related to the inverse of the Laplace operator. And the energy then can be, the energy functional is the sum of two terms. So this is the first one. So the Frechet derivative is just V square. And this is the second one. The Frechet derivative is this one, and it is quadratic in F. But from the point of view of Hamiltonian dynamics, it is the you can see this quadratic part as a perturbation of an integrable flow. I will come back to this later. Okay, so I would like to say something about the time discretization of this equation. So as I said, the flow of such an equation is essentially an exponential. Because if you remember, if you are here, so dtg is equal to add h of g, and it means that, I mean, you have, of course, to give a meaning to this exponential, and usually you have to truncate. So it will be in the sense of asymptotic expansion. But if you want to do numerics, in some sense, it is the same as solving, imagine that now Y is a huge matrix, it is the same as solving this. And you imagine that this is an equation set on a Lie group, for example, because A has a structure, for example, skew symmetric. And you have tons of methods. So the very first one is, for example, to freeze here this guy here and to solve the exponential. And at the level of the PDE, it means that if you have fn of xv, which is supposed to be an approximation of the exact solution at the time n tau, then you freeze this and you solve this equation starting in fn, and then you end up with fn plus 1. So this is typically the kind of method that you would use. And so formally, essentially, you can write this, right? This is essentially this. So the problem here is how do you compute what is here the exponential? So how do you compute the solution of this equation? So if you fix h, how do you compute this? I mean, the solution, you know what it is. You just use characteristics as in the first slide, and you have the solution. The problem is how to compute it. And these are essentially the three ways to do this. Either you completely discretize. So h is given. You want to have a solution of this equation in short time, for example. So either you discretize completely in time using finite differences, a spectral method. But then you essentially you have troubles because this is an unbounded operator. So if you discretize, you will have a very severe restriction in the time step. You can use particle method. Essentially you drop some particle and you let them evolve through the flow and you try to get some information. So the problem is in the dropping particle because you have a statistical noise. And you have semi-Lagrangian method, which are so the idea is now you fix the grid, and you use characteristics to move the point of the grid, and then you project on the grid. And the main problem here is that so if yj are the point of a grid, and if you let this point evolve through a flow, then you do not end up in the grid. So you have to make some interpolation. And when you make an interpolation, you create some numerical viscosity, and you lose completely the Hamiltonian structure. And so typically, you will get tau to the p, which is essentially the precision of your scheme, and a space error, which accumulates this way, which is due to the interpolation. Because at each step, you make an interpolation error, delta xr. But you can play with this R, and in fact use extremely high R. So a semi-Lagrangian method are in some sense very close to sorry, I just okay. So okay, well, I will come back to this later. Okay, so now I will talk about the Vlasov-Poisson and the Vlasov HMF equations. So here I would like to mention a very interesting reference by Kurt in 52. Do you know this, Nader? So we were reading with Nicolas Crouzet, we were reading some literature about the Vlasov equations. Okay, so these old references. And I think it is between Jordansky and Arseniev, or between Arseniev and Horst, I don't remember. You had a reference on a paper by Kurt, and then this reference disappears. and you never see it again in the literature. And this guy is an astronomer in Basel. I'm not sure if he's alive. He went to Purdue, I think, and then he's probably, if he lives, he's probably more than 100. And he wrote tons of books, but everything in German. So, so there is a paper by Kurt where you have a proof of existence of the Vlasov equation. Very nice, 52. Okay, right. So, so if you have other name to mention, to drop out, it's a moment.
There must be a Russian reference.
Of course. Of course, of course, of course.
This is like in Sobolev space.
It's the same?
You're also missing Pfaffenmoser on that.
Pfaffenmoser, yes. Okay, just to see. I forgot Pfaffenmoser to see if someone would have mentioned him. Thank you. Okay, so but so the existence theorem I just want to mention is because I will work in such spaces. So so these are the standard regularity in the Sobolev sense, but I will have to control also the moments. Yes, comment on dit? Support of the in some sense, the support of the function. And in fact, so here, typically, this is the kind of result that you have. Essentially, this is it was first written by Pierre de Gon. So if you start in some high Sobolev norm, then you're locally Lipschitz in a Sobolev norm in a lower of a lower index and only bounded in this norm for a finite time. Okay, so essentially, if you are smooth enough, you have local existence for in high Sobolev indices. And this, if you want to do numerical analysis, this is enough. Because if you want to have a convergence proof, then it is enough. So here I just write down. So what are the best schemes for the Vlasov-Poisson equations? I think that they are based on this decomposition between the free field, so the linear flow, and the nonlinear flow. And as in many examples, in fact, you can solve them explicitly up to space discretization. So for this one, it's clear. It is just a characteristic exact solution. And for this one, it's like in the cubic Schrödinger equation. You have, if you look at the nonlinear part, in fact, the modulus is constant if you just solve it alone. And here it's the same. If you look at this equation without the velocity here, in fact, you can prove that this phi is constant because it is just it does not depend here. If you change u to u plus something that depends on x, then it does not change. So you have two exact solution, and then you can make some high order splitting. So you combine these two, and you use Becker-Campbell-Hausdorff formula, and you can derive very high order methods. So essentially, you increase the time error. So you decrease the time error. And if you use Lagrange, semi-Lagrangian method, then you can use high order Lagrange interpolation. So the R of delta x to the R can be essentially arbitrarily large. And this is 17 that is used. Okay, and okay, so typically, so these two slides just to finish to talk about the numerical analysis. So in some sense, there is a theorem that produces many papers. But the theorem is that if you have a PDE that is locally Lipschitz, and well posed in in some space HS, and if you use a method of order of classical order P, then you have that's the f at times t minus a numerical solution in HS is bounded by a constant that depends on a finite time, tau p, and of course something f naught in HS plus 100 or okay, so S prime with S prime. So this is really a typical convergence proof, a typical convergence result for a PDE. You fix the finite time. Tau is a discretization parameter, so T equals n tau. So you fix the finite time. You lose some regularity here in the estimates, and then you have convergence. But if you compare with the classical mechanics case, this is in classical mechanics, of course, HS and HS prime could be compared. But so it's interesting only if you want to compute exactly a trajectory, which was done in the ITs, for example. So if you want to send a satellite to the moon or to bomb a city, you have to be extremely precise. Hopefully, I don't know, but but of course, this constant here is exponential of exponential of exponential of t in some cases. I mean, in the classical case, it's just exponential of t, but you can have an extremely large constant here at this level. And if you want to compute the trajectory here, it means that for a long time, it means that you will have to take tau essentially exponential of minus t, so you just cannot. Yeah. So now if you want to increase the time, it is a much more delicate question. You know that you will lose the trajectory, but you want to have some global feature of the flow that is preserved. And this is the history of this question, in fact. So it started especially in astronomy and in molecular dynamics, because in molecular dynamics you have tons of possible trajectories. You have molecules moving everywhere, so the numerical scheme cannot catch them, absolutely not. But what you want to know is the global property of the molecule. So what you want to know is more so what is more important for the physicist is do I have a preservation of the energy? Do I have a preservation of the momentum? Do I have stability of the periodic solutions? And so in the 90s, it was these symplectic integrators in the case of classical mechanics were more and more used. And it was only in the 90s that we understood why you have a much better behavior for symplectic integrators. And the proof of this, I mean, the important thing here is that if you use a symplectic integrator, in fact, it is a very old. I mean, it goes back to Moser in '68. Which says that if you imagine that you have a map like this, which is close to identity and symplectic, then essentially phi tau coincides with the exact flow phi tilde at time tau, where phi tilde here is the solution of a Hamiltonian system. Okay. So it is a Hamiltonian. So if you imagine that you have a discrete but symplectic trajectory, what Moser said is that okay, you can in fact interpolate this trajectory using a Hamiltonian flow independent of the time, because you can always do this if you allow some time dependence here. But independently on the time, it is much more difficult. And you have to pay this by an exponentially small term. And so Moser just wrote in this 68 paper, okay, it works. And then it was only Benetin and Giorgili in the 90s who proved that, wrote rigorously the estimates with the exponential remainder term. And then it was also proved by Heirer and Lubitsch in the end of the 90s. So it means that if you have a symplectic integrator, then you have an energy. You have a modified energy, which is close to the exact one. And this energy is preserved. And once you have a preserved energy, then you can play. Then you can use energy method if you want to prove some stability in the Lyapunov sense. You can do KM theory in infinite dimensions. And this was extended to semi-linear PDE like Schrödinger and waves. Essentially by me and Benoît and Dario for the soliton. So in this case, you also have, essentially this is an extension of this theorem to PDE, but you have to, you need a CFL condition. So you have a restriction between the time and the space control. And in all of this, you have some numerical resonance that appear. And the numerical resonance, you can understand them very easily. Imagine that you have something like this. So, okay, plus maybe plus some nonlinearity, and lambda is a huge matrix. If you want to understand the behavior of this, the problem is to look at the possible resonance of this lambda. Just in the linear case, so in KM theory, or if you do some averaging, essentially you have to control all these sort of guys. They have to be different from zero. But in fact, the object, if you do some numerical analysis, this is not this, but this is why at the level of the flow, this is exponential of tau times lambda. But you fix tau. So essentially, this is the map. Of course, here in this case, this is the exact flow. But imagine that you have two matrices like here. Then you will approximate this by this. Okay. So in fact, you not only have these resonances, but all the resonances that come here. And now you are on a circle. So you have much more possible resonances. It's not this, but more like tau multiplied by lambda 1 plus lambda p has to be away from 2 pi integers. So you have special numerical resonances. So that was the situation. And so now the next goal was to extend this to this nonlinear transport equation. So the very first question is, what is the analog of perturbation theory, so like KM theory, averaging? What is the analog for Vlasov equations? If you take the nonlinear Schrödinger equation, if you look at the solitons, you need an energy to prove orbital stability. So you need what do we need for Vlasov equations? So now I'm going to show you some typical behaviors of nonlinear transport equations. So the very first one is, so I will just consider the Euler equation, and I will start with the Kolmogorov flow. So Kolmogorov flow, I think it's this one. So it is known to be unstable. So you start with your semi-Lagrangian scheme. This is in vorticity. Okay, so the numerical scheme is lost. You have creation of smaller structures, but they are killed by the numerical dissipation. And then you end up with something, and this something is very particular because it looks periodic in time. So this is a This is funny. It looks like a von Karman alley, and then it is extremely stable because you see you can so you go to time to this time 1000. Right? So it is extremely stable. So it means that they exist because now we are computing really the Euler equation and not the Navier-Stokes because of the numerical velocity, because of the numerical dissipation. Because now, in some sense, in this time interval, you can apply a convergence result and prove that now you have a solution of the Euler. I won't do this, of course, but. So you have, it seems that you have many periodic solutions to the Euler equation, and that they are stable. Here is another funny example. Which one is this? Is it? This is this one. So at the beginning, I for some personal reasons, I glue two Gaussians on an almost flat shear flow. And then if you let this evolve, you have the very same behavior, which means turbulent. For some reason that I cannot explain, the solution remains localized, and you have some periodic solution. It's more delicate to see, but it is not anymore in a x or y direction. It is more like a turning solution, but you have a stability again. And so if you look now at
so this is periodic in both x
of
and
course,
y?
yes.
Both x and y.
Yeah. And these are the plots of the Fourier transform of this solution. So you look at the mode and the evolution of the mode with respect to time. So in red, this is the absolute value of the mode, and in blue and green, these are the real and imaginary part. So you see that you have a turbulent period, and then it is completely stable and completely periodic. And if you make a frequency analysis using some tools, numerical tools, you can actually compute the period and see that this is completely periodic. And if you increase the size of the mode, so mode 2.1, mode 3.1, what you can observe is that the period here is the turbulent period is more and more long. So this is typical for a typical phenomena for a weak convergence, which means that the speed of convergence depends on the size of the mode, on the level of the mode. So let's make a conjecture. So this is the good thing of conjecture, is that you can say most of the solutions, in some sense, are weakly damped towards quasi-periodic solutions. And in fact, the first question is, do we have periodic solutions? And in fact, it's very easy to construct periodic solutions to the Euler equations. This was surprising. I was not. It was not existing, but it's a stupid remark. But if you compare with the Schrödinger equation, where you have to use Km or Neschmoser to prove the existence of periodic solutions, here you just take a shear flow. With a flat part, so that explains the. So you take a shear flow like this, hop, with a flat part. So this is 0 here. Omega is 0 in this zone, and then you complete by a periodic boundary condition. And here you glue an invariant, a stationary state of the 2D Euler with compact support on R2, and then it travels at a speed that depends, in fact, of the flow. Because here it is you are in a region such that you have this, and the velocity. It means that the velocity here is constant and in this direction. So you can construct tori of any dimension in the 2D Euler. Of course, the question to know if they are stable or not is much more complicated. Okay, so now what happens for the Vlasov case? So for the Vlasov case, then in this case we can actually prove expect. I mean, this is probably one of the only example where we can prove some such kind of results. So weak damping towards something. But this is essentially due to the fact that if you look at this operator here, dt plus vdx, it is completely integrable, and you have some damping. So which is the Landau damping, and it was proved essentially by Mou and Villani the first time that it is stable if you by nonlinear perturbation. So for the Vlasov case. So I just would like to show you what it means. Okay, so this just explain this slide. So if you look at the free flow, so the solution of this equation, then the solution is explicit. If you compute the HS norm of the solution, then you have it goes to infinity when time is goes to infinity. So you have creation of oscillations. But if you look in Fourier, then you just have it is a solitary wave in Fourier. In fact, the k Fourier coefficient is just a solitary wave that moves at the speed k. And the Landau damping is just saying that if you look at this object, because f is smooth, f naught is smooth, then you have this decay. So you converge to 0, so when t goes to infinity, but at a speed here that depends on k. So this is essentially what we observed for the Euler equation. But in a much more complicated setting for Euler, because we were converging toward periodic solutions, while here we converge towards stationary states. But let's. I'm going to show you some what it means. Okay. So here I start with a solution that is essentially this one. Sinus 4x multiplied by a Gaussian in V, and then I let the free flow evolve. So here this is in x and v. So x is here and v is here. So okay, you have creation of small structures, delicate to interpolate. Numerical problems here that you can see, but in Fourier it's just two bubbles that travel. And the Landau damping is just saying that, okay, if you fix here the mode, 0, 2 is just a scale. So if you fix the mode, then at some point you see nothing because the packet just disappeared. So the weak convergence just means that if you fix a level, for example, this one here, then you weakly converge towards 0 in this case, just because the packet fly away. Okay, so this is for the free flow, and now what happens in the HMF case? Vlasov first, Vlasov-Poisson. So if you turn on the nonlinearity, so you have a similar phenomena, but you have creation of modes in X. So these are the modes in X. So essentially you have this is the mode plus and minus 4. So you create plus and minus 8 and the mode 0. And the mode 0 is not damped. So if you do not depend on X, you do not travel in Fourier. So this is just an illustration of the result that you weakly converge towards something that is essentially that depends only on V. So you have these nonlinear exchanges, but in the end it is more or less like the free flow. And so it reminds me a lot the fact that if you perturb a completely integrable system in classical mechanics, then essentially you generically remains integrable. So there is an analogy with this. So the Vlasov HMF model that I will consider is just the case where you have only one mode in the nonlinearity. I remember. Here, you have only one mode, so this is just cosinus, and not the inverse of the Laplace operator. And in this case, I will just show you the sort of thing that we observe. In this case, this is again the same. And this is exactly the same picture as for the Vlasov-Poisson case. So it really retains the same thing, but it is much more simple. It is a much more simple model. Okay, so these are okay. So this is just a slide concerning the existing result on the long time behavior of the Vlasov and Euler equation. Okay, so essentially, I just explained this, right? So essentially, it means that if you turn on the nonlinearity, if you work around some stable states that depends only on V, then you behave like the free flow. Essentially, this is what it means. And there is an extension in the case of Euler, but for the Quet flow. So not for periodic solution, but for the Quet flow by Nader and Jacob. Okay, so I just explain because I would like to too many things to say. Huh? I just would like to explain you the strategy. So the idea is, so you have this Vlasov HMF equation, and you look at this function. So you just take the pullback. F is the so you work. R is a perturbation of a stationary state that depends only on V. This is a stationary state, and you pull it back by the free flow. So essentially, here, what you look, this G, this is just in terms of. So if you consider that the energy is the sum of H, the total energy is the sum of H naught plus, let's say, epsilon P. No. So this one is just integral of V square times F, and this one is integral of F. Okay. Then essentially this G is just this thing. Okay. So it is a scattering operator. And so you write down the equation for this V, and you see that it's if you imagine that eta is 0, it just changes the potential by a time-dependent potential, and it depends on the time this way. So here you recognize the exact flow of the nonlinear part. So essentially, what it means is that this is essentially I have a slide on this later. Sorry. Okay, and then if you want to have some estimates on this term, and the final result is a scattering result. Huh? It's a scattering result in the sense that when t goes to infinity, this has a limit that depends on x and v. Okay, so the originality of the Vlasov HMF model is that we can work with Sobolev regularity. So I will not enter into these details, but in the Mouon-Villani and then Bedrosian, Mouot, and Masmoudi, you use Gevrey or analytic regularity. In the HMF case, because you have a very smooth kernel, you can use Sobolev. So this is essentially the idea, and then you do not have an exponential decay, but an algebraic decay that depends on the Sobolev regularity. But this is a scattering result. And so it means that, in fact, this guy has a limit. And I would like to... so this result implies the Landau damping in the sense that if you go back to the original variable, so if you take this G, and if you go back to the original variable, and if you look them in Fourier, then you have the same decay as for the free flow. Which means that if this is the solution of the Vlasov equation, then essentially what the scattering results say is that f of h0 plus epsilon p for large team is the same as the free flow, more or less. I mean, if you start with some f naught here, you will have a modified, which is essentially another way of writing down the scattering result. But for the NLS case, for example, this guy is very well defined. Now, this is just exponential of IT delta, so you can invert it In the other case, in the Vlasov case, this guy is better seen in Fourier than in X and V. I will not explain you the idea in many details because I would like to. Essentially, the idea is this one. If you look at the equation, at this equation, if you forget eta, so it is a nonlinear but time-driven nonlinear transport equation, and this it depends on G only through this coefficient gk, which is the Fourier transform of G. K is in X, and this is in V. Gk of kt, and the argument is just if gk is stable, then it is smooth. Then I have a decay of g hat. So I have a decay in t. So here I have essentially 1 over t to the s in front of this guy. So I can make the integral converge. And when I can make the integral converge, I have some regularity. And it's a bootstrap argument. It's a bootstrap argument. This is essentially, so then you have to cook a norm to explain this bootstrap argument, and which is essentially the same as you use for Euler, but only with fewer stages. But okay, so now I would like to explain this in terms of normal forms, because I have been searching for a normal form transform for 2 years, just to discover that in fact so now the idea is, okay, you can see the Vlasov equation as a perturbation of an integrable flow, and then you try to solve some homological equation, I don't know. So you try to reduce the flow. For example, to change this by an h tilde naught plus epsilon square. This is what you would do in KM theory. And in fact, the best choice is to use this transformation here. Phi h0 minus m and phi h0 plus epsilon p plus m. So essentially this guy at a time m large, at a large time m. So in fact, if you try to find the best change of variable, you will end up with this transformation, but at a large time m, not completely large, but large. And the effect of this is contained in this formula. So if you look at, so if you imagine that this is a transformation, exactly like normal forms, you preserve the Hamiltonian structure, and so you look at the shape of the energy after the transformation. So essentially, you compute this, but this guy preserves this energy, and h0, it's preserved by this flow. So essentially, the new energy is this one. So you just change P by P composed with the free flow. And P composed with the free flow, in the Vlasov case, it is a very good object, because you essentially have this gk of km, because it is the time. This is the guy that we have in the right-hand side. And so you see that if m is large, then this guy is very small. So the effect of the free flow is to weaken the nonlinearity. And when you if you now try to make some iterations of this, then you will choose m. For example, well, okay, sorry for this numerology, but this is epsilon to the minus 1 over 7, makes that this guy is square root of epsilon close to the identity. This you can imagine. If you go for a time that is, let's say, 1 over square root of epsilon, then you see a little bit the nonlinearity, but not too much. So you are still close to identity because epsilon is small, but you are still large. So you can essentially you can go up to m equals epsilon to the minus 7, and then you can iterate the process, because here this is evolution after the time m, and here in this case the nonlinearity is dump, and then you can go and do exactly like km iterations. Okay, but it was the first proof. But unfortunately, we found the norm in the end, and with the norm is direct. You do not need to have all this machinery, but I like this machinery, so I like to present it. Because it might be helpful in some cases to use these things and to hope to have something like Birkhoff, so for long enough time, but you cannot exactly make the convergence. Maybe there is a case where it's more flexible in some sense. Okay. Okay, and then essentially, when we obtain this result, we obtain the result for the numerical schemes. But I would like to end with something funny. I find this funny, sorry. This is, if you start, so this is still HMF, but you start with a too large in the focusing case, and you start with a too large initial data, for example. So essentially, like for Euler, you start with something unstable, and you end up with something periodic in time. Here, if you do this, you observe this kind of picture, and this picture is essentially this one that is well known. No. Okay. So this is the phase space of the pendulum. And in fact, so of course here it's a bad simulation because you have too much numerical viscosity. And it turns out that there exist for HMF stationary states that are under this form of V square plus M0. So there are such guys that are stable in the Lyapunov sense. And so, and there is a hope now to do the same, to prove the same sort of result around these stationary states. Why? Because in 2D everybody is integrable. So if you look at this system, then you can put it to an action angle variable. And this is integrability of the pendulum. And in 2D, this is you can essentially, at least locally, always do this. That's why maybe 2D Euler is integrable. Maybe this is because of this. And if you look at omega, as a function of A, then it is something like this. So of course A here is positive, and it is something like this. Okay, this is omega of A. So essentially, in the good variables, the free flow is A and theta plus T omega A, which looks very much like the TV that we had, but with omega that is not linear. But if we have no flat part here, we can expect some decay. But the only problem is here, when you are close to the harmonic oscillator. Because when you are close to the harmonic oscillator, you cannot really you cannot have damping. So it means that you have, at least for this guy, you have a damping that is blocked to 1 over T2. You cannot have more, you cannot have exponential or 1 over Ts. It's 1 over T2 because of this point. Here it's okay because omega is very, it moves, so you completely stretch, you dump. But close to the origin, close to the harmonic oscillator, you have problems. I will stop. Okay. Voilà. Thank you.
Obviously, we have the break afterwards, so we can take time for some questions. No question? Everybody wants coffee?
So between the HMF model and the full Vlasov-Poisson model, you could have kernel which is not as somehow intermediate. Do you think you could get something there in finite regularity?
Yes, but yes and no, which means I don't know. But what is sure is that we have if we have n0 modes, then instead of having here we lose 4 for regularity index, so here you will lose something that depends on n naught. So after that you can try to optimize, but I don't want to play this game, I think. For me, more interesting is if you are between HMF and Euler. So if you allow the kernel to depend a little bit on the velocity, maybe not too much, maybe with compact support, very nice. But I mean, there is a world between. Essentially, we are looking at one. Okay, so. But you have a real singularity in the Euler equation because the kernel depends on V, on X, and it is singular in X and V. So it would be a nice toy model, but I don't know if there are some physicists interested by some models. But,
Okay. No more questions. Let's answer them again.
thank you.